The Earth is falling right now, quietly, continuously, yet it never reaches the sun. Its path is neither still nor straight. It is a long, soft curve woven into the fabric of space-time itself, a balance so precise that it feels like stillness. Even as you breathe, our world is drifting through gravity's embrace, not pulled downward, not flung outward, but held in a silent negotiation that has lasted for billions of years. Before we begin, if this calm journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a quiet tap on subscribe helps me continue creating these night voyages, and it means more than you know. Now we drift into the first set of ideas. Part 1. The illusion of falling in space. Even though Earth is constantly being pulled toward the sun, it never gets closer. Instead, it traces a continuous arc around it, a motion so steady that it feels like stillness. In space, falling does not always mean moving downward. Sometimes it means drifting forever along the curve of gravity. If you could step outside the solar system and watch Earth move, you would see a world in perpetual descent. Every second, our planet is pulled inward by the sun's gravity, a force 28 times stronger than Earth's own. If nothing opposed it, Earth would plunge directly toward the sun in a long spiral, crossing the gulf of space in a matter of months. But that never happens. Instead, Earth glides sideways fast enough that its fall becomes a circle. This balance creates the quiet illusion we live inside every day, the illusion that nothing is happening at all. You never feel this fall. The oceans feel no tug. The mountains do not lean. The air does not sweep across continents as though the planet were plunging downward. Everything moves together, locked into the same freefall. As Newton understood, motion that is shared is motion that disappears from perception. We experience acceleration, not steady drift, and the Earth's drift is as smooth as polished glass. Nothing interrupts it, nothing shakes it. So even though every living being on Earth is falling through space, it feels like rest. This is one of the most profound truths in orbital mechanics. An orbit is simply falling with enough forward motion that you never reach the thing pulling you. Gravity bends your path, but motion bends it back. This combination, this soft curve, is what we call an orbit, but the word hides the simplicity of what's really happening. Earth is not circling like a runner tracing a track. It's falling, continuously, silently, and forever. To understand how this works, imagine standing on a high mountain with a perfect empty horizon. If you threw a stone gently, it would arc downward and hit the ground. Throw it harder and the arc widens. Harder still and it travels farther before falling. Isaac Newton imagined this centuries ago. If you threw a stone fast enough, so fast that it curved downward at the same rate Earth's surface curved away beneath it, then the stone would never land at all. It would fall around the world indefinitely. Earth is that stone. Every second of its journey is a careful balancing act between the sun's inward pull and Earth's sideways motion of about 30 kilometers per second. That speed is not arbitrary. It's the exact velocity required to fall without crashing. If Earth moved even slightly slower, gravity would dominate and our planet would spiral inward over millions of years. If it moved faster, the balance would tip the other way. Earth would drift outward, escaping the sun entirely. Our world is held in a narrow band of stability, a cosmic equilibrium shaped by the early solar system's chaotic birth. This sideways motion, this ancient inheritance, is what saves us from the sun. Long before Earth existed, the cloud of gas and dust that became the solar system was turning, slowly at first, then faster as it collapsed under gravity. This is the same phenomenon that makes an ice skater spin faster by pulling in their arms. Angular momentum must be conserved. Everything inside that spinning cloud inherited its rotation. The sun spins, the planets spin, their moons spin, and all the planets carry forward the sideways motion that allowed them to settle into long, graceful orbits instead of falling directly inward. This motion is not an addition to gravity. It is a partner to it. When we call an orbit stable, we're really saying something quiet and profound. The fall and the flight are perfectly matched. If you could watch Earth's orbit slowed down to a crawl, you might expect to see a circular path. But Earth does not move in a perfect circle. It traces an ellipse, slightly stretched, coming a little closer to the Sun in January and drifting slightly farther away in July. These variations change Earth's orbital speed, faster at perihelion, slower at aphelion, and yet the balance never breaks. The ellipse is simply the geometry of a fall shaped by an uneven distance. Gravity adjusts, motion adjusts, the dance continues. This understanding reveals something subtle. Falling in space has no up or down. It is not a drop. It is not a plunge. It is a path shaped by the curvature of space-time. Einstein showed that gravity is not a pull, but a bending. The Sun curves the fabric of space around it, and Earth follows the straightest possible path through that curved geometry. To us, the path looks curved, but to Earth, it feels like motion in a straight line. This is one of the deeper illusions. Not only is Earth falling, it is falling along what feels like the most natural, simplest possible trajectory. Orbit, in this sense, is not a struggle against gravity. It is the expression of gravity. You can see this illusion on the International Space Station. Astronauts are falling around Earth in the same way Earth falls around the Sun. Because they fall together with their spacecraft, they experience weightlessness, even as gravity is still acting on them. They are not floating because gravity has vanished. They are floating because they are in perpetual descent. The same principle applies to our planet. We are weightless with respect to the Sun because our sideways motion perfectly matches our inward fall. From this perspective, the solar system is not a set of objects locked in place. It is a system of objects continually missing each other by just the right amount. Every planet is falling, every moon is falling. Even the Sun, massive as it is, falls slightly due to the planets tugging on it. There is no still point, only balance. And balance is what gives us everything: seasons, climate, day and night. Without this delicate fall, Earth would have no steady warmth, no oceans, no life. A world that crashed into the Sun would not last long. A world that escaped into the cold darkness between stars would fare no better. We live in the narrow, quiet corridor between those extremes, kept stable by a fall that never ends. Tomorrow, when you look up at the Sun, remember that you are not sitting beneath it. You are drifting around it, held in motion by a tether made of geometry and time. The warmth you feel is not shining down onto a still world. It is illuminating a planet in motion, a world gliding through an endless curve. And as this journey continues, one question naturally follows. If Earth is falling perfectly, what force began this fall in the first place? We'll drift into that mystery next. Part 2. What an orbit really is. An orbit is not motion around something. It is motion toward something, always missing the fall by just enough to stay in balance. It is the exact speed where falling becomes flight, the quiet compromise between gravity and motion that shapes every world in our solar system. If you could watch Earth's orbit unfold as if time were slowed to a gentle drift, you would not see a planet circling like a runner on a track. You would see something softer, something stranger. Earth, forever leaning inward, forever falling, yet forever carried forward by an ancient momentum that keeps it from ever reaching the Sun. That balance is delicate, but not fragile. It is steady, persistent, and written into the laws that guide every planet, moon, and satellite in the cosmos. At its heart, an orbit is simply this: the shape that falling takes when you move forward fast enough. We often imagine gravity as a downward force, as though in space there must be a top and a bottom. But an orbit has no up or down. Instead, there is only the geometry of motion and the curvature of space-time. When a world falls through that curvature with the right speed, its path becomes curved as well, so precisely curved that it loops endlessly around the object it is falling toward. This balance begins with inertia, the quiet persistence of motion. Once something is moving, it will keep moving in a straight line unless something alters that path. Gravity is that something. It bends the path inward, pulling the moving object toward the massive body. But if the object is moving fast enough sideways, it overshoots the point it's being pulled toward. It never stops falling, but its fall becomes a continuous miss, a never-ending glide around the source of gravity. This is the essence of an orbit, forward motion that is constantly bent inward by gravity, but never enough to collide. To make this more intuitive, imagine a ball rolling across a curved surface. If the surface bends downward slightly, the ball will roll toward the dip. But if the ball is rolling fast enough to the side, it might spiral around that dip rather than plunging straight into it. The ball is always being pulled inward, but its sideways motion keeps it suspended around the center. In space, that dip is the curvature created by mass, and the ball is a planet moving through space-time. This is what Einstein meant when he said that mass tells space-time how to curve, and space-time tells matter how to move. Earth's orbit is a product of that curvature. There is no invisible string holding the planet, no force pushing it along. The sun bends space-time, and Earth simply follows the straightest possible path through that bent geometry. That path happens to be a long, almost circular loop. One of the quiet beauties of orbits is that they are not rigid. They can stretch, wobble, tilt, and shift. Earth's orbit, for example, is not a perfect circle, but a gentle ellipse. Sometimes we are slightly closer to the sun, sometimes slightly farther. These changes alter our speed, faster when near, slower when far. Johannes Kepler captured this in his second law, the law of equal areas, which says that planets sweep out equal areas in equal times. It means the planet moves faster when it's closer to the sun because gravity pulls more strongly there, and slower when farther away. But even with these variations, the underlying principle does not break. The fall and the flight remain in balance. If Earth suddenly moved faster, just a little, its orbit would widen. If it moved much faster, it could break free entirely, leaving the sun behind and drifting into interstellar space. Escape velocity is the speed where motion wins over gravity. A planet that crosses that boundary no longer falls inward at all. If Earth slowed down instead, even slightly, it would begin a slow inward spiral, creeping closer to the sun over millions of years. The fall would finally overpower the flight. The Earth's current speed, about 30 kilometers per second, is the exact compromise required for a stable trajectory. Not too fast, not too slow. This precision is not coincidence. It is inherited motion, the remnant momentum from the swirling cloud that formed the solar system. That ancient rotation shaped every orbit we see today. Conservation of angular momentum ensured that nothing fell straight inward. Everything spun, everything drifted, everything found a path between falling and flying. If you want to see this idea at work in daily life, look at a satellite. A satellite stays aloft for the same reason Earth remains in orbit. It is constantly falling toward Earth, but its sideways speed is so fast that the surface curves away beneath it at exactly the rate it falls. A spacecraft in low Earth orbit is not floating. It is falling, continuously, precisely, without ever reaching the ground. Astronauts experience weightlessness not because gravity is gone, but because they are in perfect freefall. The same principle holds for the Moon, for Jupiter's moons, for Saturn's rings, for the Earth itself. Every object bound by gravity is engaged in this quiet dance. Even galaxies orbit the centers of their own mass, and stars orbit the centers of galaxies. An orbit is not a planetary special case. It is the natural state of motion in a universe built on mass, motion, and symmetry. Orbits also reveal the gentle strength of gravity. At Earth's distance, the sun's pull is enough to keep us moving in a wide curve, but not enough to drag us inward. Farther out, planets need slower speeds to remain in balance. Neptune drifts around the sun at a pace far slower than Earth, but still moves fast enough to stay afloat in the sun's gravitational well. Closer in, Mercury must race forward at extraordinary speed to avoid falling inward, completing an orbit in just 88 days. Each world finds its own equilibrium, the speed that matches the strength of the sun's pull at its distance. This balance is so elegant that it is easy to forget how dynamic it really is. Earth's orbit is slowly changing. The gravitational tugs of other planets shift our path by small amounts. The Moon's pull gradually slows Earth's rotation, which indirectly alters the orbit over millions of years. The Sun itself loses mass over time, which causes Earth's orbit to expand slightly. Orbits are not static. They are alive with subtle interactions. But through all these changes, the underlying rule remains unchanged. An orbit is the shape created when falling and moving forward become the same motion. The result is motion that feels like stillness, and stillness that is motion. Day after day, year after year, Earth follows this path without effort, without energy expenditure, without correction. An orbit requires no fuel. Once established, it sustains itself through the very forces that created it. When we see the sun rise and set, we are watching the consequence of that motion. When we experience seasons, tides, and the rhythm of the calendar, we are experiencing the product of that balance. Without Earth's orbit, without this gentle compromise, we would not be here to witness any of it. So the next time you picture the Earth moving around the sun, imagine instead a world falling forever, guided by space-time, carried by momentum, held in balance by gravity's soft pull. Our orbit is not a circle drawn in space. It is a path written in the geometry of the universe. And as we follow this curve deeper, another question arises. If orbit is just perpetual falling, why does gravity bend motion at all? We drift into that next. Part 3. The role of momentum. Why Earth never spirals in. If Earth ever stopped moving sideways, even for a moment, it would plunge straight into the sun. But its ancient momentum, inherited from the swirling cloud that formed the solar system, keeps it gliding forward. Gravity bends that forward motion into a circle, not a collision. This simple idea, momentum guiding motion, gravity bending motion, is one of the quiet pillars of celestial mechanics. It's the reason planets orbit stars, moons orbit planets, and satellites orbit Earth. It is the reason our world hasn't fallen inward over billions of years. And it is the reason that falling in space is almost never a straight descent. Momentum is the universe's way of preserving motion once it begins. In the absence of friction, resistance, or collisions, motion continues forever in a straight line. This is the heart of inertia, the principle Newton wrote so clearly. An object in motion stays in motion unless acted upon by an external force. On Earth, we rarely see this happen. Air slows objects down, friction stops wheels from rolling forever, surfaces catch and resist. But in space, there is nothing to slow a planet's sideways motion, no atmosphere to drag against, no ground to push against, no medium to dissolve the speed. The sideways motion Earth carries is ancient, older than the continents, older than the oceans, older than the planet itself. It is a memory from the time before Earth existed. To understand this momentum, we go back to the very beginning. Billions of years ago, the early solar system was nothing like the organized structure we know today. It was a cloud, wide, cold, diffuse, made of gas, dust, and fragments left behind from earlier generations of stars. This cloud rotated slowly, almost imperceptibly. But as gravity pulled the cloud inward, it began to spin faster, just like a figure skater pulling in their arms. Angular momentum cannot vanish, it can only redistribute. As the cloud collapsed, the rotation tightened. This rotation eventually flattened the cloud into a disk, thinner than a single sheet of paper compared to its width, called the protoplanetary disk. Inside this disk, the sun formed at the center. The planets formed within the same spinning structure. Every planet inherited this motion. Earth was born into rotation, born into orbit, born already in motion around the newborn sun. This inherited motion is the sideways speed Earth still carries now. It is not thrusting itself forward by force. It is not powered by anything. It is simply continuing a journey that began before its surface cooled, before the first oceans formed, before the first cell sparked to life. This is momentum, the persistence of cosmic history carried into the present. Gravity, meanwhile, does its own, quiet work. It pulls everything toward everything else. The sun's gravity pulls Earth inward. But gravity does not pull Earth straight down the center like a stone dropped in a well. Instead, it continuously deflects Earth's sideways motion. Imagine a river bending around a rock. The flow of water curves smoothly around the obstacle. It never strikes the rock head-on because its sideways motion is too strong. Gravity works similarly. The sun is the massive object bending Earth's motion. Earth never hits the sun because its sideways speed is always enough to carry it forward, and gravity is always enough to bend that forward motion into a curve. The result of these two influences, sideways momentum and inward pull, is a path that loops endlessly around the sun. Earth is constantly being pulled inward, but constantly missing the sun. Not because it tries to avoid it, but because its inherited momentum never lets it fall all the way in. Momentum, in this sense, is the guardian of planets. It is also the reason why orbits must have a very specific speed. Too much sideways momentum, and Earth would not be bent enough by gravity. It would drift outward into a larger orbit, or even escape entirely. Too little, and gravity would bend the path sharply inward, spiraling Earth closer to the sun. The Earth we stand on today exists because its initial momentum was exactly right. This balance is not accidental. It is the natural result of the early solar system's formation. When the swirling disk gave birth to planets, each new world received a particular combination of distance, mass, and sideways speed. Over time, through collisions, migrations, and gravitational interactions, planets settled into stable orbits. They found paths where their momentum perfectly balanced the gravitational pull of the sun. Earth's orbit today is one of those stable paths, a narrow corridor of motion where falling and flying merge into a single continuous curve. It may sound counterintuitive, but momentum is also the reason you never feel the Earth's motion. Everything around you, your body, the oceans, the trees, the air, shares the same sideways movement. There is no change in velocity for your senses to detect. Your inner ear responds to accelerations, not steady motion. On Earth's surface, everything accelerates at the same rate toward the sun. Everything shares the same fall. Everything shares the same inherited momentum. And because everything moves together, the motion disappears from perception. It is the cosmic version of sitting in a perfectly smooth airplane. If the plane neither tilts nor shakes, your coffee stays still. You feel as though you are sitting in a quiet room. Motion becomes indistinguishable from rest. Momentum is responsible for that illusion. Even the International Space Station demonstrates this principle. It orbits Earth because it moves sideways at the exact speed where its fall matches Earth's curvature. Astronauts float because they are in freefall, not because gravity is absent. Their sideways momentum keeps them forever missing the ground below them. Earth is doing the same thing around the sun, and the sun is doing the same thing around the Milky Way. Momentum is not a force. It is a condition set at the birth of a system. The galaxy inherited it from the cloud that preceded it. The sun inherited it from the galaxy. The planets inherited it from the sun's birth disk. And we inherit it from our planet. This chain of motion stretches backward for billions of years, each generation passing its motion forward through time. Momentum is the thread connecting cosmic history. When you look at the night sky, you are seeing the evidence of this thread. Every star, every orbit, every spiral galaxy, every rotating moon, all are shaped by momentum-resisting collapse, gravity-bending motion, and the universe balancing the two into elegant, stable patterns. Earth does not spiral inward because its sideways motion never stops. No friction slows it, no atmosphere drags it. Space provides no resistance. The sun's gravity bends but never breaks that motion. As long as momentum endures, the orbit endures. This is why our world remains suspended in the quiet equilibrium that allows oceans to exist, climates to stabilize, and life to flourish. If we had inherited slightly less momentum, the Earth you know would never have formed. If we had inherited slightly more, we would orbit too far, or not at all. Every sunrise, every season, every year is a reflection of that ancient preserved motion. And as we continue this journey deeper into the mechanics of the solar system, another question gently rises. If momentum guides motion and gravity bends it, what exactly is it bending? What does the path of a planet look like in the geometry of space-time? We drift into that next. Part 4. why the sun's gravity isn't enough to pull us. And gravity is strong, but motion is stronger. Earth's sideways speed, about 30 kilometers per second, creates an outward tendency that perfectly balances the sun's inward pull. This equilibrium is delicate, ancient, and continuously maintained through the laws of motion described by Kepler and Newton. At first glance, this seems impossible. The sun is unimaginably massive, holding 99–86% of all the mass in the solar system. Its gravity sculpts the paths of planets, guides comets, and binds everything in its domain. By all intuition, Earth should fall inward, slowly but inevitably, consumed by the star that gives it life. And yet it never does. For billions of years, it has remained suspended in a long, gentle arc around the sun, neither drifting away nor drawing closer, each year tracing almost the same path it traced the year before. The reason lies in the subtle interplay between gravity, which tries to pull Earth inward, and inertia, which tries to carry Earth forward. When these two influences match with perfect precision, something extraordinary happens. A stable orbit. Earth is always falling toward the sun, but always moving fast enough sideways that it misses the sun with every moment of its descent. Imagine pulling a stone around on a string. If you let go while swinging it, the stone doesn't fly inward, it flies outward, not because it resists your hand, but because its natural motion is a straight line. Gravity plays a similar role to that guiding hand, except the string is not a rope. It's the curvature of space-time itself. Earth follows this curvature, not out of force, but out of geometry. The sun bends space, and Earth moves forward, forever missing the center. This gentle balance can be described in two ways: the classical view of Newton and the geometric view of Einstein. Newton imagined gravity as a force, an invisible pull between masses. Einstein imagined it as the shape of space-time, a bending of the cosmic fabric. Both views describe the same reality. Earth is held in an exquisite equilibrium between falling in and flying away. If Earth moved slower, just a little, the sun would win. The inward pull would dominate the sideways drift, and our planet would begin a slow spiral toward the star. Over millions of years, the orbit would contract, temperatures would rise, seasons would distort. Eventually, Earth would be consumed. A planet cannot simply exist near a star without the right speed. It would either fall inward or fail to bind at all. If Earth moved faster, just a little, the opposite would happen. The outward motion would dominate, and gravity would no longer bend the path enough to keep Earth tethered. It would drift outward into a larger, colder orbit. Push it harder still, and Earth would escape the solar system entirely, carried away into interstellar space, never to return. This razor-thin boundary between escape and collapse is why Earth's speed is so critical. At roughly 30 kilometers per second, Earth is moving sideways at exactly the rate required to stay balanced, not by coincidence, not by chance, but as a result of the solar system's formation. Billions of years ago, the swirling cloud that became the sun was rotating. As it collapsed inward under gravity, that rotation intensified. The disk of gas and dust surrounding the young sun spun faster and faster, and within this disk, Earth took shape. The sideways motion Earth carries today is a remnant of that ancient rotation, a fossilized imprint of the solar system's birth. The sun's gravity is strong, but it is not infinite. Its strength diminishes with distance, weakening as the square of that distance. At Earth's orbit, gravity is exactly strong enough to bend our forward motion into a curve, but not strong enough to erase that motion. This is why Earth does not fall inward. Its inherited speed continually resists the pull. Johannes Kepler recognized this balance long before the physics behind it was understood. He observed that planets move faster when closer to the sun and slower when farther away. Newton later revealed why. The inward gravitational pull strengthens with closeness and thus must bend a faster forward motion to maintain the orbit. Farther away, the sun's pull weakens and less speed is required to sustain the balance. This is why Mercury races through its orbit in just 88 days, while Neptune takes 165 years. Each world finds its own harmony between pull and push, gravity and momentum. Earth's equilibrium is particularly stable because of another quiet detail. Our orbit is nearly circular. The less stretched an orbit is, the more balanced the gravitational and inertial forces remain throughout the year. Earth does move slightly closer and farther from the Sun, but the variation is small, just a few million kilometers out of a total of 150 million. And this small difference, though gentle, changes our orbital speed. In January, when Earth is closest, it moves a bit faster, in July, a bit slower. But each change is exactly what is required to keep the orbit continuous. Gravity adjusts the path, and momentum adjusts the speed, always in dialogue, always in balance. It's important to recognize that Earth is not locked into this orbit forever. Gravity is not static. Momentum is not eternally conserved in a closed form. Tiny influences accumulate over time. The gravitational pulls of Jupiter and Saturn subtly tug at our orbit. The Sun loses mass very slowly as it fuses hydrogen into helium, reducing its gravitational pull. Even the presence of the Moon slightly modifies our trajectory, as the Earth-Moon system orbits a shared center of mass. But these changes are slow, so slow they unfold across millions of years. Our orbit breathes gently, expanding by centimeters each year, adjusting but never drifting far from equilibrium. The balance remains. When you stand under the sky and feel nothing, no tug, no drift, no sense of motion, you are experiencing the remarkable stability of this cosmic arrangement. You feel no falling toward the Sun because everything around you is falling at the same rate. You feel no sideways motion because everything around you shares the same inherited momentum. This shared journey creates the illusion of stillness. If gravity were slightly stronger, Earth's inward fall would overpower its drift. If it were slightly weaker, Earth's drift would overpower the fall. But in the real solar system, the numbers align in a way that sustains life, not precariously, not by chance, but by the physics of formation and the quiet rigor of orbital mechanics. This balance is not just a planetary phenomenon, it is universal. Stars orbit the centers of their galaxies using the same principle: gravity bending, momentum resisting. Galaxies themselves orbit within clusters. Even the motion of galaxies relative to the cosmic web reflects this same interplay of forces. It is a cosmic rhythm, the inward pull of gravity, the outward tendency of motion, and the equilibrium written between them. When you look at the Sun, remember that its gravity alone is not enough to claim the Earth. Our planet's sideways motion, preserved from the ancient spinning cloud, is just as important. In orbit, gravity does not win. Motion does not win. They coexist. And as we drift deeper into this cosmic voyage, one question naturally follows. If this balance is so precise, what shape does Earth's orbit take when we look closely at its imperfections? We turn to that next. Part 5. Earth's path is not a circle. The subtle stretch of an ellipse Earth moves faster in January and slower in July, tracing an elongated path first understood by Johannes Kepler. Even this imperfection does not break the orbit, it deepens it. The ellipse is the Sun's signature on the sky, a reminder that gravity is dynamic, not rigid. If you could drift above the solar system and watch Earth complete a full revolution, you'd notice something quietly surprising. Our world does not trace a perfect ring. Its path is slightly stretched, like a circle pulled gently from opposite sides, not enough to seem dramatic, not enough to distort the seasons beyond recognition, but enough to reveal a deeper truth. Gravity does not create perfect shapes. It creates balance. That small stretch is the imprint of Kepler's first law, the law of ellipses. In the early 1600s, when many still believed planetary orbits were perfect circles, Kepler studied the observations of Tycho Brahe with almost obsessive devotion. The data refused to fit a circle. No matter how he adjusted and recalculated, the numbers resisted. And so, Kepler let the universe speak for itself. What finally emerged was an ellipse, the simplest curve that could hold the Sun slightly off-center and still describe the planet's journey precisely. It was a revelation not just of mathematics, but of physical truth. The universe prefers stability over symmetry, motion over perfection. The stretch of Earth's orbit, its eccentricity, is small, about 0.11 on a scale where 0 is a perfect circle and 1 is a fully elongated line. This means Earth's orbit is almost circular, but not quite. At its closest point to the Sun, called perihelion, Earth is about 147 million kilometers away. At its farthest, aphelion, it is about 152 million kilometers away. A difference of only about 5 million kilometers, small compared to the vastness of the orbit, but large enough to influence the rhythm of time itself. This difference subtly adjusts Earth's speed. In January, when Earth is closer to the Sun, gravity is stronger and the planet moves faster, about 30.3 kilometers per second. By July, when Earth is farther away, gravity weakens slightly and our world slows to about 29.3 kilometers per second. A small difference in speed, but immense in consequence. This modulation is what allows Kepler's second law, the law of equal areas, to unfold naturally. When Earth is near perihelion, it sweeps out a long, narrow arc quickly. When it is near aphelion, it sweeps out a shorter, wider section more slowly. But the area traced over equal intervals of time remains exactly the same. This is nature's way of preserving balance. Speed adjusts where distance changes. The orbit breathes, tightening, stretching, accelerating, slowing, yet always returning to itself, never drifting away, never spiraling inward. This breath is so subtle we never feel it, but astronomers have seen it for centuries. It is inscribed in the timing of the seasons, the length of days, and the shifting position of Earth in the sky. The elliptical orbit also explains one of the quiet mysteries people often notice without understanding. The Sun appears slightly larger in winter than in summer. Not dramatically, not enough for the eye to catch without careful comparison, but enough for instruments to measure. At perihelion, the Sun's disk is about 3% larger than at aphelion. A tiny detail, yet one that connects your everyday experience to the precise geometry of Earth's path. But perhaps more importantly, the ellipse reminds us that gravity is not a rigid force. It is not something that demands perfect circles or exact symmetry. It is a shaping influence, flexible and responsive, sculpting motion according to distance and speed. The Sun does not need a perfect circle to hold Earth. It needs only the continuous negotiation between gravity and momentum. In the classical Newtonian view, this negotiation comes from the inverse square nature of gravity. The gravitational pull decreases with the square of the distance. When Earth is closer, the pull increases sharply. When farther, it weakens quickly. The orbit adapts. The planet moves faster where the Sun's grip is tighter, slower where it loosens. This interplay produces the ellipse without any need for external correction. From the perspective of Einstein's relativity, the ellipse emerges because the curvature of spacetime is not uniform. Space curves more intensely near the Sun and less intensely farther away. Earth follows the straightest possible path through this curved geometry, which, when viewed from above, transforms into a graceful oval. In either view, Newtonian or relativistic, the ellipse is not an imperfection. It is the natural shape of motion in a universe where gravity and sideways momentum coexist. This shape also has profound consequences for our seasons. We often learn that the seasons are caused only by Earth's axial tilt, not by how close we are to the Sun. And this is mostly true. Tilt is the dominant factor, but the ellipse contributes quietly. Because Earth moves faster in January, the Northern Hemisphere's winter is slightly shorter. Because Earth moves slower in July, the Northern Hemisphere's summer is slightly longer. Just a few days difference, but enough to shape ecosystems and climate patterns subtly over long timescales. This also explains why the earliest sunset does not occur on the winter solstice and the latest sunrise does not occur on the same day. Those moments drift because Earth's speed drifts. The Sun's apparent motion in the sky shifts slightly ahead or behind our clocks due to this variation, creating what astronomers call the equation of time. The ellipse is one of the reasons clocks and the Sun disagree. The ellipse influences more than just sunlight. It affects the length of Earth's year as well. Because our orbit is stretched, The time Earth takes to complete one revolution is determined not only by the circumference of its path, but also by the speed variations along the way. This is why Kepler's third law links distance and orbital period so elegantly. Planets farther from the Sun have longer paths but also move slower on average, creating predictable rhythms across the solar system. But even this ellipse is not fixed. Over long timescales, Earth's orbit gently changes shape due to gravitational interactions with other planets, especially Jupiter and Saturn. Sometimes the ellipse grows slightly more stretched, sometimes it becomes nearly circular. This slow oscillation, known as orbital eccentricity cycles, occurs over tens of thousands of years and subtly influences Earth's climate, helping drive the long cycle of ice ages and warm periods. Yet through all these shifts, one truth remains. The ellipse is stable. Its stretch is modest, its rhythm consistent, its equilibrium preserved. Earth's orbit is not fragile. It is resilient, adapting to gravitational influences without collapsing. If Earth's orbit were perfectly circular, the solar system would be less dynamic, less complex, less alive. The slight ellipse introduces variety into the movement of worlds, timing into seasons, texture into the flow of time. It is part of what makes our planet's environment stable yet gently changing, predictable yet not monotonous. When you imagine Earth moving around the Sun, picture not a perfect ring but a stretched curve shaped by ancient forces, maintained by the laws of motion and refined by the gravity of other worlds. Picture a path that breathes, not wildly but subtly, with each turn. And as we continue drifting through this quiet voyage, another question naturally emerges. If Earth's orbit is shaped by this gentle stretch, why does the motion feel completely still? What hides all this complexity from our senses? We turn to that next. Part 6. Why you never feel the motion. You are moving tens of thousands of kilometers every hour, yet you feel completely still. This stillness is an illusion born from uniform motion, where everything around you moves in perfect synchrony. There is no wind of space, no friction, no sensation of speed, only balance. If you could somehow see the path you trace through the cosmos, your body, this room, the earth beneath you, you would witness motion on an almost unimaginable scale. The Earth rotates at over 1,600 kilometers per hour at the equator. It rushes around the Sun at 30 kilometers per second. The Sun itself orbits the center of the Milky Way at nearly 500,000 miles per hour. Yet, through all of this, your breath remains steady. Your heartbeat does not falter. A still cup of water rests quietly on a table as if the entire universe were perfectly still. The reason is profound, but simple. You only feel motion when it changes. When motion is constant and shared, it vanishes from your senses. Your inner ear is a remarkable but limited instrument. It detects acceleration, not velocity. It can sense the start of motion, the push that begins it, the tilt that alters it. But once movement becomes smooth and unchanging, the sensors fall silent. This is why you feel a car lurch when it starts, but not when it cruises steadily along the highway. It's why you sense the moment an elevator begins to rise, but the ride itself feels still. It is why airplanes can fly at hundreds of miles per hour without disturbing a single droplet inside your drink. Your body evolved to navigate a world of starts and stops, not the sweeping, uninterrupted arcs of planetary motion. The accelerations you experience while walking, climbing, or turning your head are millions of times stronger than the gentle, constant accelerations caused by Earth's motion through space. The biological machinery inside you is simply not designed to detect them. But there's another layer to this stillness, one even more fundamental. Everything around you shares the motion. The air, the oceans, the buildings, the trees, they all move with Earth's rotation and orbit. They inherit the same momentum, share the same equilibrium, and experience the same smooth trajectory. There is no relative difference for your senses to measure, no air rushing backward to signal that Earth is spinning, no tug of inertia to indicate the Earth is falling around the Sun. If something moved differently, if the ground beneath you slipped away or the air lagged behind, you would immediately notice. But the Earth does not lose speed. The motion never ceases. It is perfectly uniform. The stillness you feel is really the absence of change. One of the most elegant demonstrations of this illusion was made in 1851 by Léon Foucault. He suspended a heavy pendulum inside a tall room and set it swinging. Over hours, the pendulum's path slowly rotated, not because the pendulum changed direction, but because the Earth turned beneath it. The pendulum revealed motion your body cannot detect. It showed that the floor, the building, the entire planet was rotating, even though no wind blew, no ground shook, no sense of motion stirred within the observers. The Foucault pendulum teaches something humbling. Our senses are too small for the world we live in. Our natural perception evolved for a human scale, not a cosmic one. We are exquisitely tuned to the motion of running, balancing, climbing trees, avoiding obstacles. But the motions of planets and stars lie far outside our biological window. They are too smooth, too vast, too constant. This is why astronauts aboard the International Space Station, traveling at 17,500 miles per hour, experience weightlessness instead of motion. They orbit Earth in perfect freefall. Everything inside the station falls at the same rate, without friction, without air resistance, without uneven forces acting on their bodies. Astronauts feel nothing, not speed, not direction, not rotation, only the gentle drift of microgravity. Earth behaves the same way in the sun's gravity. The entire planet and everything on it is in freefall. We are perpetually falling, missing the sun with every instant, carried sideways by ancient momentum. Because every object around you shares this fall, you feel no downward tug, no sense of plunging inward. Freefall is indistinguishable from stillness when everything participates equally. Einstein built much of general relativity on this insight. He realized that freefall is not a force acting on you. It is the absence of any direct force. A falling astronaut feels weightless not because gravity has vanished, but because gravity is the only force acting. A person standing on the ground actually experiences more force than someone falling. The ground pushes upward against their feet. In orbit, that push disappears. Everything moves together along the natural path of space-time, and motion becomes invisible to sensation. You live in this invisible motion every moment. Consider the rotation of the Earth. At the equator, the ground beneath your feet is turning faster than the speed of sound, yet your coffee sits still. The air does not whip past. The landscape remains serene. You do not feel the planet spinning because you, the air, and the ground all rotate together. There is no friction between you and the spin, no sideways wind, no changing force, just constant motion. If the Earth suddenly stopped spinning, even for a moment, you would feel it. The atmosphere would tear across the surface at 600 kilometers per hour. The oceans would surge, the ground would heave. Not because nature is chaotic, but because the smoothness would be broken. Uniform motion would become abrupt motion, and your senses would awaken violently. The illusion of stillness is not a flaw of perception. It is the natural outcome of harmony. Everything that matters to your senses, the objects you touch, the air you breathe, moves exactly with you. On Earth, there is no turbulence, no drag, no hint of the cosmic speeds we inhabit. Our relative stillness is the calm inside the storm of celestial motion. And yet, sometimes we can glimpse hints of this hidden motion, the slow rotation of a Foucault pendulum, the drift of stars across the night sky, the shifting constellations over months, the small but measurable change in the sun's altitude throughout the year. These changes do not disrupt the stillness, but they reveal it, subtle fingerprints of motion, on the fabric of time. Ancient astronomers noticed these clues long before the laws of motion were understood. The Egyptians observed that certain stars rose earlier each night. The Babylonians tracked the uneven motion of the sun across the seasons. They saw the illusion long before they could explain it. Today, we understand not only that the Earth moves, but why the motion is invisible. Uniform motion creates no internal differences. Motion felt equally by all things cannot be felt at all. In physics, this is called the equivalence principle, and it holds true for everything from tiny laboratory experiments to the trajectories of galaxies. You are still because everything is moving with you. Your stillness is a shared equilibrium. Your calm is the reflection of cosmic balance. In this balance, the Earth rotates, orbits, and falls through space without a whisper to your senses. The silence is not the absence of motion, it is the perfection of motion. And as we follow this quiet journey further, another question rises gently from this stillness. If we never feel the motion, what does that motion look like when we step back and view it from the outside, from the scale of the solar system itself? We will drift into that next. Part 7. The quiet cooperation of gravity and inertia. Earth's orbit is a conversation between two forces, gravity pulling inward and inertia carrying it forward. Neither dominates, neither surrenders. Their balance creates the long, gentle fall that shapes every sunrise and every season. If you imagine these two influences as characters, they are not adversaries locked in struggle, nor partners dancing in total harmony. They are more like two ancient voices, speaking softly across the vastness of space. One whispers, "Come closer." The other replies, "I will continue forward." And the path Earth follows, this smooth, sweeping ellipse around the sun, is the sentence they write together, repeated endlessly across billions of years. This interplay forms the foundation of orbital mechanics. Gravity, the inward pull caused by mass, always acts toward the center. Inertia, the tendency of a moving object to continue straight ahead, always acts perpendicular to that pull. The Earth does not choose between these forces, it embodies both. Without gravity, it would travel in a straight line forever. Without inertia, it would fall inward and vanish into the sun. But with both, Earth follows a curve, a perfect natural compromise. This compromise is far deeper than a simple balance of forces. It is the framework for the structure of our solar system. Every planet, every moon, every asteroid and comet exists because this relationship holds steady across time. In the early centuries of astronomy, this motion seemed mystical. Circles were thought to be divine shapes, and orbits were imagined as perfect geometric ideals. But the truth is more subtle, more dynamic, more alive. Earth's orbit is not a rigid track, it is a living path, shaped moment by the give and take between gravity and inertia. To understand why this matters, imagine driving a car along a curved road. You feel yourself pushed outward as the curve tightens. That outward sensation is not a force acting on you, but your inertia. Your body's tendency to continue in a straight line. The car, through friction and steering, forces you to follow a new path. Earth experiences something similar, though without friction, without wheels, and without any external structure guiding its path. Instead of a road, Earth moves along the curvature of space. Instead of friction, gravity provides the inward influence. And instead of wheels, inertia supplies the forward persistence. Together, they carve a graceful orbit that requires no engine, no maintenance, no correction. Gravity and inertia cooperate so perfectly that Earth's orbital speed adjusts continually throughout the year. When Earth is closer to the Sun, gravity's inward pull increases slightly, and Earth speeds up in response. When Earth is farther away, gravity's pull weakens, and inertia allows the planet to slow. The result is not chaos, but a predictable rhythm, a natural acceleration and deceleration that keep the orbit stable. This adjustment is not conscious, it is not commanded, it arises directly from physics, the same physics that governs a stone swung on a string or a satellite circling Earth. But because the Earth-Sun connection spans nearly 150 million kilometers, the scale at which this cooperation plays out is vast, slow, and deeply serene. You can see its effects in the changing seasons, not only because Earth's tilt defines the distribution of light across hemispheres, but also because the subtle variations in Earth's orbital speed shift the lengths of seasons slightly. Northern Hemisphere winters are shorter because Earth moves faster when closer to the Sun. Summers are a little longer because Earth moves slower when farther away. These seasonal patterns, which shape every ecosystem on the planet, arise partly from the quiet negotiation between gravity and inertia. Another place this cooperation reveals itself is in the tides. The ocean is pulled by the moon, but also by the sun's gravitational influence. Solar tides are weaker, yet they modulate the lunar tides in gentle cycles, spring tides and neap tides that repeat every 2 weeks. Even these subtle shifts reflect the interconnectedness of orbital motion. Gravity is never isolated. It acts everywhere, on everything, all at once. Inertia, too, leaves its imprint. It is the reason Earth rotates, the reason day follows night in a steady rhythm. That rotation, once faster in the ancient past, has slowed over billions of years due to the Moon's gravitational pull. But the inertia contained within Earth's spin continues to define the length of day, the behavior of weather systems, and the stability of our planet's shape. Gravity and inertia are not opposing forces. They are complementary aspects of motion. Gravity shapes the path. Inertia carries the motion forward. This is why the solar system is not static. Everything is moving. The planets orbit the sun. The sun orbits the center of the Milky Way. The Milky Way drifts through the cosmic web. Even the tiny particles inside atoms spin and vibrate, carrying their own intrinsic motion. Stillness, in this universe, is an illusion, one created by scale, by smoothness, and by shared trajectories. This brings us to a deeper layer of understanding. The orbit itself is the natural motion of a world falling freely in a curved space-time. Einstein reimagined gravity not as an invisible tug, but as the geometry of the universe. Massive objects curve the space around them, and smaller objects follow straight paths within that curvature. To us, the path looks curved. To Earth, the path feels straight. In this view, gravity does not pull inward. Inertia does not push forward. They are not forces opposed. They are aspects of a single phenomenon, an object following the straightest possible route through a curved landscape. Imagine a marble rolling inside a bowl. If the bowl is perfectly shaped, the marble moves in a curved path without any motor or guidance. It does not feel forced off its path. It simply follows the natural contour of the surface. Earth follows the contour of space-time in the same way. The shape of its orbit is a reflection of the sun's mass bending the geometry around it. But the comparison ends there because the bowl does not reshape itself. The sun, however, generates a gravitational field that extends infinitely, growing weaker with distance but never vanishing. Inertia presses outward, gravity curves that outward motion inward, and the result, the space between those two influences, is the orbit we see. This cooperation is quiet, but it permeates everything. If gravity were slightly stronger, inertia would not be enough to maintain the orbit. If inertia were slightly greater, gravity would not bend the path sufficiently. But the actual numbers set during the solar system's formation create a balance that has endured for billions of years. This endurance is remarkable. A planet's orbit is not a fragile structure, it is resilient. Only a catastrophic event, a nearby passing star, a massive reconfiguration of the solar system, could break it. Small perturbations from other planets create tiny oscillations, but the fundamental shape holds. Gravity holds the orbit together. Inertia keeps it expanded. Each sunrise is born from this balance. Each year is defined by it. Every season, every migration, every biological cycle is shaped by this quiet cooperation. And as we drift deeper into this cosmic story, another question arises gently from the shadows of the orbit. If gravity and inertia define Earth's motion around the sun, then what larger motion carries both of them together as the sun itself journeys through the galaxy? We turn to that next. Part 8. The sun is moving. 2. The orbit within orbits. While Earth circles the sun circles the center of the Milky Way, and the galaxy itself drifts through space. Every orbit is nested inside another, each one shaped by larger motions. We are falling around a star that is falling around a galaxy that is falling through the cosmos. It's tempting to imagine the solar system as a tidy, isolated mechanism, the sun at the center, planets orbiting it in predictable curves, each world moving in its own stable lane. But the deeper truth is far more dynamic. The sun is not a stationary anchor. It is itself in motion, sweeping through the galaxy in a vast spiraling orbit that takes hundreds of millions of years to complete. And as it travels, it carries every planet with it, including Earth. We are not orbiting in place. we are gliding through space in a complex, layered journey. If you could step outside the Milky Way and watch from afar, you would see our solar system tracing a long, elegant path around the galactic center. The Sun moves at roughly 220 kilometers per second, completing one galactic revolution every 230 million years. This means that during the entire age of the dinosaurs, Earth completed only one orbit around the galaxy. Humanity arrived in the cosmic theater just moments ago, at the very end of that immense galactic year. In this grand motion, Earth's orbit around the Sun looks like a tiny loop embroidered on a vast ribbon. This nested structure, an orbit within an orbit, is not unique. It is the architecture of the universe. Electrons orbit atomic nuclei, moons orbit planets, planets orbit stars, stars orbit galactic centers, and galaxies themselves move along gravitational currents through cosmic filaments shaped by dark matter. Motion is layered, continuous, and interconnected. To understand why the Sun moves, we need only consider mass. As with any gravitational system, the Milky Way's center, where a supermassive black hole resides, creates a deep gravitational well. But the black hole is not the sole influencer. The combined mass of hundreds of billions of stars, enormous clouds of gas, and vast halos of dark matter all contribute to the gravitational landscape. The Sun moves through this landscape not because it chooses to, but because gravity shapes the geometry of motion on every scale. And just like Earth around the Sun does not feel its own orbit. There is no galactic wind rushing past, no sense of turning or spinning. The motion is uniform, smooth, ancient. The entire solar system shares it. Every comet, every asteroid, every gas molecule in the heliosphere moves together through that galactic arc. There is no internal disturbance, only a quiet collective drift. This motion gives rise to a remarkable perspective. Even as Earth falls around the Sun and everything around it falls in a much larger curve. Imagine standing on a small boat drifting down a slow-moving river. If you walk around the deck, you are following your own path relative to the boat, but the boat itself is flowing with the river, carried by a larger motion, and the river, in turn, winds through the landscape on its way to the sea. Each movement contains another. Each frame of reference sits within a broader one. This layered motion is what the solar system experiences on cosmic scales. Earth is walking its orbit on a drifting boat. The Sun is the boat. The Milky Way is the river. But even this metaphor understates the complexity. The Milky Way itself is not fixed. It drifts through the local group, a cluster of galaxies dominated by two giants, the Milky Way and Andromeda. These galaxies are on a slow-motion collision course, approaching each other at about 110 kilometers per second. In roughly 4 to 5 billion years, they will merge, forming a new, larger galaxy. During that immense reshaping, the Sun's orbit will shift, distort, and eventually settle into a new path. So Earth's journey is not just around the Sun or around the Milky Way. It is part of an evolving, dynamic cosmic dance involving entire galaxies. And beyond even that motion, the local group itself flows toward a larger gravitational attraction, the Virgo cluster. And that cluster, in turn, drifts toward an even greater concentration of mass called the Laniakea supercluster, a region of space so immense it contains 100,000 galaxies. And Laniakea, too, is falling toward something even larger, the Great Attractor, a mysterious region of mass so great that it bends the motion of galaxies across hundreds of millions of light years. The universe is not static. It is a web of motion upon motion. Every orbit sits within a larger gravitational landscape. The path we take around the Sun is altered slightly by the Sun's motion around the Milky Way. The Milky Way's path is influenced subtly by interactions with neighboring galaxies. Even the paths of galaxies are shaped by dark matter, whose invisible scaffolding threads through the cosmos like a hidden skeleton. This is why scientists often describe motion in space using the term freefall. Everything is falling along the curvature of space-time created by mass, whether that mass is the Sun, the Milky Way's core, or the massive galaxy clusters beyond. Freefall is not a failure of support. It is the most natural motion the universe allows. This multi-layered falling also explains why no celestial object moves in a perfect circle. Ellipses, spirals, drifts, oscillations, these are the signatures of a universe shaped by many gravitational influences at once. Earth's orbit is slightly stretched because Jupiter's gravity tugs on it. The Sun's orbit around the Milky Way wobbles gently as it moves through regions of varying density. The Milky Way itself is distorted by tidal forces from Andromeda's gravity. The cosmic dance is orderly, but not rigid. And through all of these motions, you feel none of it. You feel no pull toward the galactic center because everything around you shares the same acceleration. You feel no drift toward the Virgo cluster because that motion is spread across millions of light years. You experience only local forces, those that cause relative changes. Uniform cosmic motion remains silent, invisible to the senses. Stillness, on the scale of human perception, is only the absence of change. But from a cosmic perspective, we are always moving. We are carried by currents older and wider than memory, each orbit layered on top of another, each motion weaving into a larger one. Our path is not a circle or even an ellipse. It is a long, spiraling stream through the galaxy, stitched with smaller loops and arcs created by the planet's orbits. If you could trace Earth's path in 3 dimensions over millions of years, it would resemble a helix, spiraling through the galaxy as it follows the Sun's orbit. And that helix itself would drift as the Milky Way moves. The result is a thread through space, a wandering line stretching across the cosmos, never repeating, never resting, never truly still. This is the journey you are on now. You are orbiting a moving star inside a moving galaxy, inside a moving cluster. And as we drift deeper into the understanding of motion, another question arises quietly. If the Sun moves through the galaxy, why does Earth not simply slip away? What keeps our world tethered so securely to a moving star? We turn to that next. Part 9. Why Earth doesn't escape. Instead, if Earth moved much faster, it would break free entirely, but its speed is precise, fast enough to avoid falling inward, slow enough to avoid drifting away. This boundary is called escape velocity, a threshold that defines whether gravity holds you or releases you. To understand why Earth remains bound to the Sun instead of flying off into the dark, you must first imagine gravity not as a chain that pulls objects in, but as a well carved into the fabric of space-time. Massive objects like stars create deep depressions, and smaller objects fall into those depressions. But falling into a gravitational well does not always mean sinking to the center. If something has enough sideways speed, it can skim the curved walls and remain suspended in a perpetual loop, never sinking and never escaping. This is what Earth does. In this picture, escape velocity is the speed required to climb out of the well entirely. It is the threshold where a world no longer loops around the Sun but drifts away, its path straightening into a long, gentle line through the galaxy. For Earth, escape velocity from the Sun at our distance is about 42 kilometers per second. We currently move at roughly 30. That difference, those 12 kilometers per second, is the margin that keeps us tethered to our star. 12 kilometers per second in cosmic terms is very small. It is the difference between a bound world and a wandering one. It is the line between a sunrise and an endless night. It is the threshold that determines whether Earth remains part of the solar system or becomes a rogue planet drifting alone through interstellar space. This boundary is not arbitrary. It arises naturally from the laws of motion. Newton described it through the balance of kinetic and potential energy. Einstein described it through space-time curvature. Both perspectives reveal the same truth. Gravity can hold you only as long as your motion does not overcome the depth of its well. If Earth suddenly gained a small but significant amount of additional sideways speed, say from a massive impact or an extraordinary gravitational encounter, it would begin to drift outward. The orbit would stretch into a longer ellipse. Seasons would lengthen and cool. Over millions of years, the path could expand until Earth was no longer bound at all. The sun would simply shrink in the sky, growing smaller with each passing millennium until it was only a star among stars. Conversely, if Earth slowed, the orbit would collapse inward. We explored that possibility earlier, but the key point is this: speed determines fate. The exact speed Earth possesses, the exact energy it carries, decides whether it remains in orbit, spirals inward, or breaks away. This precarious balance might sound fragile, but it is not. Earth's speed is preserved not by chance, but by conservation of angular momentum, one of the most unbreakable principles in physics. Angular momentum cannot disappear. It cannot be destroyed. It can only move from one form to another. Earth inherited its momentum billions of years ago during the formation of the solar system, and nothing since has taken enough of that motion away to change its orbit dramatically. Even significant gravitational interactions, such as those from Jupiter, the largest planet, do not threaten Earth's stability. Jupiter tugs on Earth during each orbit, and Earth tugs back. But these exchanges are tiny compared to the total momentum of the system. They cause small oscillations, cycles that repeat over thousands of years, but they never come close to pushing Earth past the escape boundary. Inertia, in this sense, is Earth's protector. Another way to understand escape is to imagine throwing a ball upward. If you throw it lightly, it rises and falls back down. Throw it harder, and it rises higher before falling. Throw it even harder, and it might reach the edge of the atmosphere before gravity pulls it back. But if you throw it at about 11 kilometers per second, it will never come back. That is Earth's escape velocity relative to its own gravity. Now, imagine replacing your arm with the early solar system, the ball with Earth, and the throw with the initial sideways speed Earth inherited. That throw was the swirling motion of the protoplanetary disk, the ancient spin of the collapsing cloud of gas and dust. The velocity Earth emerged with was not random. It was the natural result of that vast, rotating environment. In this sense, the question of why Earth doesn't escape becomes, why did Earth form with the speed it has? And the answer is, because the physics of the early solar system gave it no other choice. The orbits of all planets reflect the angular momentum distribution of the disk they formed from. Closer to the Sun, the disk rotated faster, farther out, slower. Each planet settled into a speed that made sense for its distance. Earth's speed is not arbitrary. It is the speed required for a body of its mass at its distance to remain in a stable orbit. If Earth had formed faster, it would not have remained where it is. If it had formed slower, it would have drifted inward. The solar system itself shaped what was possible. This is why even dramatic events in Earth's history, the giant impact that formed the Moon, the bombardment of comets and asteroids, the slow tug of war between Earth and its satellite, never pushed Earth anywhere near the escape threshold. The amount of momentum required to unbind a planet is beyond the reach of anything that has happened in the last 4 billion years. Escape velocity also reveals something about the Sun. The Sun's mass creates a gravitational field deep enough to hold planets across vast distances, yet even the Sun's gravity does not impose itself infinitely. Farther out, the edge of the solar system is defined by a boundary called the Hill sphere, the region where the Sun's gravity dominates over the gravity of other stars. Within that region, planets remain bound. Outside it, the influence of the Sun fades. Earth sits deep within that sphere, far from its edges, far from the region where gravitational competition becomes intense. We remain securely tethered not only by our speed, but by our position within the Sun's gravitational domain. There's another, subtler aspect to why Earth never escapes. Space is quiet. There is nothing to push Earth faster, no friction, no gas clouds thick enough to slow us or speed us up, no stellar winds capable of altering our orbit at scale. The spaces between stars are almost perfectly empty. Earth is not buffeted by external forces. Its motion persists with astonishing stability. Even the gradual loss of mass from the Sun, through the steady flow of charged particles in the solar wind and the slow conversion of mass into energy, barely changes Earth's orbit. Over billions of years, Earth drifts outward by only a tiny amount because of this. but the drift is far too small to matter in human or even geological timescales. In the end, Earth remains because the universe respects balance. Our world's speed is neither excessive nor insufficient. It is a precise inherited compromise, a speed sculpted by gravity, preserved by momentum, and sheltered by the vast emptiness of space. And yet, even with all this stability, one question quietly lingers. If Earth's speed determines whether it stays bound to the sun, then where did that speed come from? Where did the swirling motion that shaped every planet truly begin? We drift into that next. Part 10. How the early solar system set everything in motion. Billions of years ago, the sun and planets formed from a spinning cloud of gas and dust. As that cloud collapsed under gravity, it rotated faster, conserving angular momentum. Every orbit we see today, Earth's included, is a fossilized remnant of that ancient spin. To imagine the beginning of the solar system, picture a vast darkness filled with a drifting cloud, cold, quiet, and so diffuse that each particle was separated by kilometers. It was not yet a system, not yet a family of worlds. It was simply a slowly turning mist left over from the deaths of earlier stars. And yet inside this cloud lay the seeds of everything familiar. The sun, the planets, the moons, even the rocky atoms beneath your feet. This cloud, known as the solar nebula, was unimaginably large, so wide that if you placed a sphere around it, that sphere would stretch beyond the modern orbits of the outer planets. Within it, hydrogen and helium dominated, but small grains of heavier elements drifted silently, created in supernova explosions long before the sun existed. For millions of years, the nebula floated in equilibrium, neither collapsing nor expanding significantly. Then, something disturbed it. Perhaps a nearby supernova shockwave, perhaps the gravitational influence of a passing star, perhaps merely the inevitable drift of matter pooling under its own weight. Whatever the cause, the calm was broken. The cloud began to collapse. As it collapsed, something subtle but essential happened. It spun faster. Angular momentum is one of the universe's most unyielding principles. When a system contracts, it must speed up. A figure skater pulling in her arms turns faster. A shrinking cloud behaves the same way. That slow rotation quickened, becoming a gentle whirl, then a broad swirl, then a spinning disk that flattened under its own motion. This rotation is the key to everything that followed. It prevented all the material from falling straight inward. Instead, it formed a disk, thin, wide, and steadily spinning. At the center of this disk, matter accumulated rapidly, building pressure and heat. The more it accumulated, the hotter it became. Eventually, conditions at the center grew extreme enough for nuclear fusion to ignite. The sun was born in a flash of light that illuminated the swirling disk around it. Even then, the solar system was not yet formed. The disk still held vast amounts of gas and dust, moving in smooth, circular paths around the newborn star. Tiny grains collided and stuck, creating larger clumps. Those clumps merged into boulders, those boulders into mountains, and those mountains into planetary embryos, worlds in their infancy, orbiting in the same direction as the original nebula's spin. The orbits of the planets today, Earth included, reflect the momentum of that ancient whirlpool. Earth formed from the dust and ice within this rotating disk. Every particle that contributed to Earth's mass carried angular momentum. Those particles spiraled inward, colliding, heating, merging, but never losing the essential direction of their motion. As Earth grew, it inherited the combined angular momentum of millions of collisions. The direction of Earth's orbit, the direction of Earth's rotation, even the tilt of its axis, all trace back to that primordial spin. But the early solar system was not calm. It was chaotic, turbulent, filled with collisions on a scale almost impossible to imagine. Protoplanets smashed into each other, altering their spins and shifting their orbits. Earth itself experienced at least one giant impact, the collision with an object the size of Mars that likely formed the Moon. Yet even this catastrophic event did not erase the underlying angular momentum of the system. It redistributed it, shaping the Earth-Moon relationship, but preserving the solar system's overall direction. Angular momentum, once present, cannot simply vanish. It is conserved. It must go somewhere. And in the cosmic architecture of the solar system, it manifests as motion, rotation, revolution, orbit. The sun spins, Earth orbits. The planets trace paths set in motion before they ever existed. To understand how fundamental this is, imagine a universe without angular momentum. Every collapsing cloud would fall straight inward. No disks, no planets, no moons, no stable orbits. Stars might still form, but planetary systems would not. Rotation is the difference between a universe of wandering rocks and a universe filled with structured worlds. This is why rotation seems to appear everywhere. From hurricanes spiraling on Earth to galaxies swirling across billions of light years, the patterns of nature echo the first motions of collapsing clouds. Angular momentum is not merely a quirk of physics. It is a rule that underlies the formation of structure itself. In the early solar system, that structure was messy. The planets we see today did not begin in their modern positions. They migrated, shifting inward and outward as they interacted with the gas disk. Jupiter, the giant among them, moved first inward, then outward, reshaping the orbits of every world nearby. Saturn followed. Uranus and Neptune likely formed closer to the Sun and drifted outward over millions of years. But even during this migration, this slow rearrangement of worlds, the underlying direction of motion remained the same. The planets kept orbiting the Sun in the same broad orientation. Their speeds differed, their distances changed, but the momentum inherited from the solar nebula continued to guide their paths. Earth's orbit today is a memory of that timing, a fossil of motion, a relic preserved across billions of years. If you could see the early solar system in time-lapse, you would witness a swirling storm slowly settling into order. Dust, gathering into bands, planetesimals carving gaps, worlds sweeping clean their orbits. Eventually, the disk would thin, the remaining gas would be blown away by the sun's early winds. And what would remain is what we know today. A star at the center, planets in motion, each orbiting with a speed and distance dictated by its share of the nebula's ancient spin. This is why Earth moves at 30 kilometers per second, why it orbits at 150 million kilometers, why it falls around the sun instead of into it. These are not random numbers. They are the natural consequences of formation. Even now, billions of years later, the solar system still carries faint reminders of its rotating birth. The sun itself spins approximately once every 27 days at its equator. The planets trace orbits that lie roughly on the same plane, the plane of the old protoplanetary disk. Even the direction of Earth's rotation matches the direction of the nebula's spin. Every second of every day, the history of the solar system moves beneath your feet. When you watch a sunrise, you are seeing the rotation given to Earth by the swirling disk that formed it. When you mark the passing of a year, you are measuring Earth's journey through the path that disk set into motion. When you look through a telescope and see Jupiter's moons circling it, or Saturn's rings turning, you are glimpsing the universal trace of angular momentum. It is all connected. Motion is memory. Every orbit is an inheritance. And as we drift deeper into this cosmic history, another quiet question rises. If angular momentum set the solar system in motion, what subtle geometry does that motion create as Earth falls through space? We turn to that next. Part 11. The geometry of freefall. An orbit is just freefall with a twist. Throw a ball hard enough and it will arc. Throw it harder and the arc widens. At exactly the right speed, the arc matches the curvature of Earth. That same geometry scales upward. Earth falls along a path that curves around the sun itself. If you picture freefall, you might imagine something dropping straight down. A stone released from your hand, a leaf drifting toward the ground, a raindrop tumbling through the air. But in the language of physics, freefall has nothing to do with direction. It has nothing to do with down. Freefall is simply motion under gravity alone, with no other forces interfering. When nothing resists or redirects, gravity defines the path. On Earth's surface, this path is almost always a downward line because the planet blocks the fall. But remove the surface, remove the air, remove every obstacle that interrupts motion. What remains is the purest expression of gravity's guidance, a curve shaped by the geometry of space. Earth, the moon, satellites, the countless fragments drifting through the solar system, all of them are in free fall, not falling downward, but falling around. To understand this idea, imagine standing on a high cliff with a perfectly spherical world beneath you. If you gently nudge a ball off the edge, it will fall almost straight down. Push it harder and it will land farther away. Harder still, and it will trace a long arc before touching the ground. Keep increasing the speed, and something remarkable happens. The ball falls toward the planet, but the ground curves away beneath it. At exactly the right speed, about 7.8 kilometers per second, the ball will fall with just the right curvature that the planet's surface drops away at the same rate. It is falling. It is always falling. But it never hits the ground. That is an orbit. The ball is not flying. It is not floating. It is simply falling in such a way that the fall becomes a loop. The same geometry applies to Earth around the Sun. Earth is constantly being pulled inward by the Sun's gravity, but its sideways motion, its ancient momentum inherited from the solar system's birth, curves that fall into a long, stable orbit. The geometry of freefall scales from a thrown rock to an entire planet. The principle is unchanged. Only the scale expands. This view of orbits as freefall is not just a convenient analogy. It is one of the most profound insights in physics. It reveals that orbits do not require effort. They do not require thrust. They do not require constant adjustment. Once an object reaches the correct speed and direction, gravity does the rest. The universe holds it in balance through the simple, unbroken geometry of falling. What changes in the transition from a ball on Earth to a planet around a star is the shape of the environment. On a small scale, gravity pulls toward the center of a sphere. On a cosmic scale, gravity shapes the curvature of space-time itself. This is Einstein's insight, that massive objects deform the geometry around them, creating valleys and slopes not made of rock or soil, but of space-time. Smaller objects then follow the straightest possible paths within that curved geometry. From our perspective, those straight paths appear curved, but to the object moving along them, the path feels natural, effortless, like moving through stillness. Earth is not being forced into its orbit, it is simply following the shape of space-time. In Newton's language, inertia carries Earth forward, gravity bends that forward motion inward. In Einstein's language, Earth moves in a straight line, but the geometry of space-time warps the definition of straight. Both interpretations describe the same reality. One uses force, one uses geometry. But both reveal the astonishing fact that an orbit is freefall in disguise. This is why astronauts aboard the International Space Station feel weightless. They are falling around Earth in the same way Earth falls around the Sun. Their fall is continuous, with no ground to stop it. Because they share the same fall as the station, they experience no pressure on their bodies, no sense of downward acceleration. They are in perpetual descent, yet that descent becomes a kind of stillness. Freefall erases the sensation of gravity even as gravity defines the motion. This paradox can feel strange because, in everyday life, falling is brief and abrupt. It is something we try to avoid. But in space, where nothing interrupts motion, freefall is gentle, smooth, and endless. It becomes not a plunge, but a path shaped by geometry. That geometry also explains why orbits are not perfect circles. A circle requires a precise, continuous inward pull matched by a perfectly consistent sideways speed. But real systems are messy. The Sun's gravity varies with distance. The interactions with other planets introduce tiny perturbations. The distribution of mass inside the Sun itself shifts over time. The result is an ellipse, a stretched circle that reflects the slightly uneven curvature of the solar system's gravitational basin. The ellipse is simply the natural curve of freefall under a varying inward pull. When Earth is closer to the Sun, gravity is stronger and the inward curvature increases. Earth speeds up to maintain the balance. When Earth is farther, gravity weakens and the curvature relaxes. Earth slows down. This change in speed is another manifestation of freefall's geometry. The path adapts to the gravitational landscape. Freefall, in this sense, is not rigid. It is flexible, adjusting its arc according to the distribution of mass. It is responsive, alive, a curve shaped moment by the interplay of motion and gravity. If you could see Earth's orbit traced in glowing lines through space, you would not see a perfect ring. You would see a delicate, slightly stretched curve, bending inward and outward in response to the sun's gravitational field. You would see the influence of Jupiter subtly tugging Earth's path, the gravitational tide of the moon adjusting the Earth-Moon barycenter, the sun's own motion creating small oscillations as the solar system moves through the galaxy. All of this complexity is contained within what we simply call freefall. And yet, from where you stand, on the surface of Earth, you feel none of it. The geometry is too large for your senses to perceive. The motion is too smooth. The fall is too perfectly shared. You experience the stability, but not the motion that creates it. Stillness, in a cosmic context, is simply freefall without friction. You are moving along a curved path shaped by forces that act continuously and invisibly. You never feel the curvature because it is the curvature of space-time itself. You never feel the fall because everything around you falls with you. The geometry of freefall is the quiet architecture beneath every sunrise, every season, every year. It is the unseen guide shaping Earth's motion around the sun, the moon's motion around Earth, the sun's motion around the Milky Way. It is a pattern repeated from subatomic particles to galaxies that spiral like giant whirlpools of light. This geometry does not end at the boundaries of the solar system. It continues outward, defining the paths of comets that fall toward the sun and swing back into the distant reaches of the Oort cloud. It shapes the arcs of asteroids, the spirals of galaxies, the trajectories of interstellar visitors like Oumuamua. Everywhere gravity acts, freefall writes its curves. And in this quiet, endless choreography of falling and curving, one question emerges gently. If this geometry guides Earth so perfectly, how does it connect to the deeper nature of gravity itself, this invisible sculptor of motion? We drift into that next. Part 12. The invisible curvature of space-time. Einstein revealed that gravity is not a force pulling downward, but a bending of space-time. Earth is not held by a tether. It is following the straightest possible path through a curved geometry. What feels like orbit is really the shape of space guiding the shape of motion. To understand this idea, imagine standing on a landscape so vast and smooth that its slopes are invisible. You do not see the contour beneath your feet, but you feel its influence gently. Now, remove the ground itself. Remove the air. Remove the blue sky, the trees, the soil. What remains is something that cannot be touched or seen, yet shapes everything: the geometry of space-time. Gravity, in Einstein's vision, is not an invisible hand pulling objects. It is the curvature of the very stage upon which the universe unfolds. Mass bends space-time. Space-time guides motion. This was one of the most profound shifts in human understanding. Before Einstein, gravity was imagined as a force acting through distance. After Einstein, it became a property of the fabric of reality. Earth's orbit is a consequence of this curvature. Earth is not held in place. It is not forced to move around the sun. It is simply moving along the straightest possible path that space-time allows in the presence of a massive star. This path looks curved to us because we are accustomed to Euclidean geometry: straight lines, flat surfaces, right angles. But space-time does not obey those rules. It stretches, flexes, and wraps itself around mass. Where space is more curved, motion appears more bent. Where space is flatter, motion appears straighter. Earth's orbit, in this sense, is not a choice or a constraint. It is the natural expression of the geometry that the sun creates. If you could visualize space-time around the sun, you might imagine a vast, gently sloping valley. Earth moves along the contour of that valley, not because something pulls it inward, but because the valley defines where straight ahead is. Just as a marble rolling along a curved surface follows the shape of the surface, Earth follows the shape of space-time. Yet the marble analogy is incomplete because the marble is held to the surface by gravity. In reality, Earth's surface is not material, it is geometry itself. Einstein's insight began with a simple thought experiment. What would it feel like to fall freely? If you were inside a falling elevator, isolated from the outside world, you would feel weightless. Everything would float beside you. This sensation is identical to the experience of orbit. Freefall erases weight. It reveals gravity's true nature. From this insight came the equivalence principle. Locally, freefall is indistinguishable from the absence of gravity. Gravity appears only when motion is prevented. When you stand on the ground, the Earth pushes upward on you. That upward push creates the sensation of weight, but in orbit, where nothing pushes, gravity becomes silent, invisible, not gone, but perfectly shared. Earth's orbit is that perfect sharing of freefall. The planet falls continuously around the sun. The ground does not get in the way. No surface interrupts the motion. The fall becomes endless, smooth, unbroken. This is the geometry of space-time at work. The curvature around the sun is not dramatic. It is gentle, subtle, so slight that you could travel millions of kilometers before noticing any significant change. But space-time does not need dramatic slopes to sculpt motion. Even a mild curvature spread across great distances can redirect the paths of planets, shape the structure of galaxies, and bend the light of distant stars. This bending of light, gravitational lensing, is one of the most beautiful consequences of curved space-time. Light travels the straightest possible route, just as planets do. But if space-time is curved, the straightest route is not a straight line. It bends. During a solar eclipse in 1919, starlight passing near the sun shifted position slightly in the sky. This shift, measured by Eddington's expeditions, was the first dramatic proof that Einstein's theory was correct. Planets, stars, galaxies, all of them follow these curved paths. On cosmic scales, motion becomes a tapestry woven by geometry. Earth's orbit around the sun is one thread in that tapestry. If the sun were heavier, the curvature would be deeper, and Earth's orbit would be tighter. If the sun were lighter, the curvature would be shallower, and Earth would drift outward. The sun's mass determines the shape of the spacetime it creates, and Earth responds with motion. This is why the orbit feels stable. The curvature around the sun is steady. It changes only as the sun slowly ages, shedding mass through sunlight and the solar wind. Over long timescales, this changes Earth's distance slightly, but not enough to alter the fundamental geometry. Spacetime curvature also explains why orbits precess. Earth's orbit shifts slowly over centuries, rotating the ellipse by tiny degrees. Mercury's orbit shifts even more because it lies deeper in the sun's gravitational well. Newtonian physics could not explain Mercury's unusual precession, but Einstein's geometry did. The curvature of spacetime near the sun alters the definitions of straightness and circularity, causing orbit paths to drift over time. Even the wobble of stars around black holes, the spiraling patterns of galaxies, the cosmic web stretching across the universe, these are all shaped by invisible curvature. But perhaps the most profound idea in relativity is that spacetime is not an empty stage. It is dynamic. Matter tells spacetime how to curve, and spacetime tells matter how to move. This relationship is the foundation of gravitational motion. Earth's orbit is not imposed upon it. It is the simplest path permitted by the geometry Earth inhabits. This geometry has layers. Near Earth, the curvature comes mostly from Earth itself. Farther out, the sun's curvature dominates. Across tens of thousands of astronomical units, the Milky Way's curvature takes over. And beyond that, on intergalactic scales, spacetime is shaped by massive galaxies, galaxy clusters, and the mysterious influence of dark matter. You are not simply standing on a planet. You're standing on a wrinkle in spacetime. That wrinkle moves, it shifts, it carries you through the galaxy, and because its curvature is smooth, you feel none of its motion. You are part of the geometry itself. To live inside spacetime is to be shaped by its curves without ever seeing the landscape directly. The effects are visible: sunrise, sunset, the changing seasons, but the cause remains invisible. You never see spacetime bend, you see the motion it creates. This invisible architecture guides everything: the fall of a meteor, the the turning of the moon, the orbit of Earth, the spiraling arms of the Milky Way. Every motion is a response to curvature. And yet, even with all this understanding, a question still lingers gently at the edge of thought. If space-time guides motion, then how do we know where this curvature begins? How do we measure something we cannot see? We drift into that next. Part 13. The subtle variations that shape the seasons. Because Earth's orbit is not perfectly circular, its distance and speed change throughout the year. These variations shift the length of days and alter the sun's apparent motion, creating the delicate timing behind solstices, equinoxes, and the seasons themselves. We often imagine the seasons as simple, predictable markers, the turning points of the year, repeating with quiet certainty. Winter deepens, spring awakens, summer lifts into fullness, and autumn drifts toward rest. But behind this familiar rhythm lies a tapestry of subtle variations woven into Earth's path around the sun. These variations are small, so small you could live your entire life without sensing them directly. Yet they shape everything from the length of days to the timing of migrations to the ebb and flow of ecosystems. And they all trace back to one quiet truth. Earth does not move around the sun in a perfect circle. It follows a stretched curve, an ellipse, and this stretch breathes through the year. When Earth is closest to the sun, a moment called perihelion, gravity pulls a little harder. Earth moves slightly faster. The days pass just a bit more quickly. When Earth is farthest, at aphelion, the gravitational pull weakens, the orbit widens, and Earth moves more slowly. These changes do not disrupt the balance of the orbit, but they do add texture to time. They lengthen one season, shorten another, shift the sun's path by subtle degrees. This is why the seasons are not equal in length. Northern Hemisphere winter is the shortest season because it occurs when Earth is nearest the sun, rushing through that portion of its orbit with slightly greater speed. Summer is the longest because Earth moves more slowly when farther from the sun. Spring and autumn fall in between, their lengths shaped by this interplay of distance and motion. It may seem counterintuitive that winter arrives when Earth is closest to the sun, but distance plays only a supporting role in temperature. The primary cause of seasons is Earth's axial tilt, the 23.5-degree lean that causes sunlight to spread differently across hemispheres. Yet even this tilt interacts with Earth's elliptical orbit in subtle, beautiful ways. When Earth moves faster near perihelion, sunlight travels across the sky more quickly each day. The sun's height changes faster. The times of sunrise and sunset drift more noticeably. This is why one of the quiet confusions of the seasons arises. The earliest sunset doesn't happen on the winter solstice. The latest sunrise doesn't either. Instead, both shift by days or even weeks because Earth's orbital speed alters the sun's apparent motion across our sky. This interaction creates what astronomers call the equation of time, a small difference between solar time, the sun's true position in the sky, and clock time, the uniform ticking of hours. This difference changes throughout the year, sometimes adding minutes, sometimes subtracting them. It is why sundials must carry subtle curves carved into their faces. It is why noon on a sundial rarely aligns perfectly with noon on a clock. These tiny adjustments shape the unfolding of the seasons with quiet precision. The solstices, the longest and shortest days of the year, occur not because Earth is closest or farthest from the sun, but because of the tilt of Earth's axis relative to its orbit. As Earth journeys along its elliptical path, the orientation of the axis remains fixed, always pointing in the same direction in space toward a distant star, Polaris. Because the axis stays aligned, the amount of sunlight each hemisphere receives shifts as Earth orbits. At the June solstice, the northern hemisphere tilts toward the sun. The sun climbs higher, days stretch long, and light lingers into the evening. At the December solstice, the northern hemisphere tilts away. The sun arcs low, shadows lengthen, and daylight fades early. These differences in sunlight drive the seasons themselves: temperature, weather patterns, plant growth, migration, the turning of life's cycles. But the timing of the solstices, The exact moment the sun reaches its highest or lowest point is influenced by Earth's elliptical orbit. The same is true of equinoxes, the moments when day and night balance evenly. Earth's speed in its orbit alters the pace at which solar longitude changes, shifting the exact timing of these balance points by hours each year. The equinoxes are not anchored solely by the tilt. They are gently guided by the breathing rhythm of Earth's elliptical path. This interplay between tilt and orbit creates subtle asymmetries everywhere. In the northern hemisphere, summer is slightly longer than winter. In the southern hemisphere, the opposite is true. Its summers occur near perihelion, making them shorter but also, on average, slightly warmer. Ocean patterns amplify or soften these differences, but their origins trace back to the way Earth moves. Even the varying lengths of days throughout the year reflect the orbit's geometry. The rate at which daylight increases after the winter solstice is not constant. The sun's path changes more quickly when Earth moves faster, more slowly when Earth moves slower. This is why the weeks after the solstice bring a noticeable rush of morning sunlight, while the approach of summer brings more gradual shifts. These variations ripple outward into the living world. Birds migrate according to day length. Trees awaken when light crosses certain thresholds. The snowpack melts in cycles, shaped partly by Earth's distance and pace. The timing of flowering plants, the quiet choreography of spring, responds not just to temperature, but to the changing quality of light, the lengthening days, the shifting height of the sun. All of these signals are braided together by the geometry of Earth's orbit. Even the changing constellations across the night sky reflect this motion. As Earth circles the sun, different portions of the galaxy become visible after sunset. The elliptical orbit alters exactly how quickly each constellation rises earlier each night. The sky drifts forward, a degree each day, but the drift is not uniform. It stretches and compresses just slightly, following the rhythm of Earth's speed. These details are small. Almost nothing in daily life reveals them directly. And yet, over weeks, months, and years, they compose the quiet music of the seasons. Earth is not simply circling the sun, it is moving through a landscape of light that changes with angle, distance, and speed. The seasons are the visible shadows of this invisible geometry. Even Earth's climate across thousands of years is influenced by variations in the shape of the orbit. The eccentricity of the ellipse changes over long timescales, stretching and relaxing in cycles shaped by interactions with Jupiter and Saturn. When the ellipse becomes more elongated, seasonal contrasts intensify. When it becomes more circular, the seasons soften. These slow cycles, Milankovitch cycles, help drive the rise and retreat of ice ages. What we experience today, this familiar turning of spring, summer, autumn, winter, is just one note in a long arc of changes stretching across hundreds of millennia. All of it begins with Earth's speed, Earth's distance, Earth's tilt, and the slight unevenness of the ellipse. And the remarkable truth is that these subtle variations do not destabilize Earth's path, they enrich it. They create texture in time, they make the seasons asymmetric, alive, unpredictable in small ways and deeply predictable in others. The year is not a perfect loop. It is a breathing, shifting, evolving shape carved by gravity and motion. And as we drift farther into this understanding of subtle cosmic influences, another question emerges softly. If these small variations shape the year so deeply, then what minute irregularities shape Earth's orbit itself across millennia? We turn to that next. Part 14. What would happen if Earth slowed down? If Earth's forward speed faded even slightly, its delicate balance would break. Our world would spiral inward over millions of years, inching closer to the sun. Temperatures would rise, seasons would distort, life would struggle, and eventually, the fall would become inevitable. Earth's orbit exists on a knife edge of motion. Too fast and we would drift outward, too slow, and the sun's gravity would begin to draw us inward. This inward spiral would not be dramatic at first. There would be no sudden plunge, no violent collapse. Instead, it would be a slow, quiet descent, the kind of change that unfolds over geological timescales, invisible to a single lifetime yet undeniable across millennia. To understand why, imagine once again the nature of orbital motion. Earth is constantly falling toward the sun, but its sideways motion is fast enough that it keeps missing the sun. If that sideways motion weakened, if the inherited momentum of billions of years began to fade, gravity would gain the slightest advantage. The orbit would shrink, not all at once, but thread by thread. The ellipse would tighten, the distance to the sun would decrease, and as Earth moved inward, the sun's gravity would grow stronger, accelerating the spiral. This feedback loop is simple yet powerful. Moving inward makes gravity stronger. Stronger gravity increases speed. Increasing speed changes the orbit. But without enough sideways motion, the new speed cannot maintain the old distance. The inward drift would begin. At first, the change would be nearly imperceptible. A difference in Earth's position too small to affect climate significantly. A shift in the length of seasons so subtle that centuries might pass before patterns began to change. But the solar system is patient. It measures time not in years but in epochs. As Earth drew closer, solar radiation would increase. The sun's brightness at our distance is not a fixed projection. It follows the inverse square law. Move 5% closer to the sun, and sunlight increases by about 10%. Move 10% closer, and the light grows by roughly 20%. These increases may sound modest, but climate systems are delicate. A small rise in solar input can trigger large shifts. Ice caps would thin, oceans would warm, weather patterns would destabilize, rainfall belts would shift, deserts would expand, forests would retreat. Seasons already tied so closely to the geometry of Earth's orbit would begin to distort. Summers would grow longer and hotter, winters shorter and warmer. Polar regions, our planet's natural coolers, would weaken dramatically. The difference between day and night temperatures would widen as the atmosphere struggled to adapt to new energy imbalances. These climatic changes would ripple outward through ecosystems. Migratory patterns would collapse. Coral reefs, already near thermal limits, would vanish. Species dependent on narrow temperature ranges would falter. Mountain habitats would shrink as temperatures rose. Even ocean currents, drivers of global climate, would begin to reorganize, perhaps slowing, perhaps intensifying, perhaps taking on patterns Earth has not seen in tens of millions of years. But the spiral would not stop. Over millions of years, Earth's orbit would continue shrinking. The day-night cycle might remain steady. Earth's rotation is tied not to orbital speed, but to angular momentum. But the calendar would change. Shorter orbits would mean shorter years. The length of time it takes Earth to complete one lap around the sun would gradually decrease. Seasonal transitions would accelerate. Imagine a world where the year's no longer 365 days, but 350, then 300, then 250. This is not fantasy. It is the natural consequence of falling deeper into the sun's gravitational well, and as the orbit shrinks, the sun grows not just brighter, but larger in the sky. A more massive presence, a dominating force. The blue sky would take on a subtly different hue as more solar energy scatters in the atmosphere. Sunrises might appear brighter, the midday glare more intense. Eventually, Earth would reach a point where the climate becomes hostile to complex life. Ocean evaporation would increase. The atmosphere would thicken with water vapor, a potent greenhouse gas. Even before Earth reached the inner regions of the solar habitable zone, runaway warming could begin. A feedback loop of humidity and heat would threaten to turn Earth into a world more like Venus, clouded, pressurized, overheated. The spiral inward would accelerate as Earth lost orbital energy. Though still slow on human scales, the pace would quicken on cosmic ones. Each decrease in orbital radius would lead to stronger gravity, which would increase orbital speed, not enough to restore the lost balance, but enough to hasten the descent. This final phase would be swift in geological terms, hundreds of thousands of years, perhaps less. The atmosphere would destabilize, oceans could begin to boil. The planet's surface, once teeming with life, would dry. Any remaining organisms would migrate toward the poles or underground, seeking refuge in shrinking pockets of survivable conditions. Even the moon's presence would not save us. As Earth fell inward, tidal forces from the sun would begin to compete with the stabilizing effects of the moon. the Earth-Moon system would start to distort. The Moon's orbit might shift slightly, a subtle echo of the deep imbalance forming between inertia and gravity. Eventually, Earth would reach a critical point where the inward pull would accelerate beyond any possibility of recovery. The planet would cross boundaries of temperature and radiation that no life could endure. The spiral would become irrevocable. And then, over one last long arc, Earth would fall, not instantly, not catastrophically, but inevitably. Its final descent would be the slow collapse of a world once balanced perfectly. In its last million years, Earth would be a scorched and barren sphere, spiraling toward a star that once nurtured life. When it reached the Sun's atmosphere, its outermost layers, it would begin to break apart. Friction with solar plasma would strip the atmosphere, melt the crust, and dissolve the remainder into the Sun's outer layers. The Earth that formed from the dust of ancient stars would return to a star. But before this fate unfolds in your imagination as something looming or imminent, it's important to remember something essential. Earth's orbit is stable, very stable. There is no natural process in the solar system capable of slowing Earth's orbital speed significantly. No atmospheric drag, no interplanetary medium thick enough to apply friction, no large body close enough to drain momentum. The Sun itself loses mass over time. If anything, Earth drifts outward, not inward. The scenario we've explored is a thought experiment, not a prediction. It is a meditation on balance, a reflection on fragility, a reminder that the stability we take for granted is the result of ancient, precise motions set in place billions of years ago. And yet this quiet exploration raises one final question. If slowing down would doom Earth, could speeding up save it or send it into a different kind of escape? We drift into that next. Part 15. Why falling forever is the most stable. Fate of all the universe prefers balance over stillness. Orbits are the natural resting state of gravity, a motion that requires no fuel, no correction, no maintenance. A planet that falls forever is not failing. It is stable. It is where physics wants it to be. Stillness, as humans imagine it, is rare in the cosmos. Our senses crave the absence of movement, quiet landscapes, unmoving horizons, a world that seems anchored in place. But nature is not built that way. Everything moves because nothing can remain perfectly at rest in a universe shaped by gravity. The only true stillness would be the absence of mass, the absence of curvature, the absence of motion itself. And that is not our universe. Instead, nature's equilibrium is motion. An orbit is not a compromise forced onto matter. It is the simplest, most efficient, most effortless state a system of gravitational bodies can reach. When gravity pulls inward and inertia carries forward, the resulting path is not tension. It is balance. A planet falling around its star forever is not struggling against collapse. It is following the geometry that requires the least resistance, the least energy, the least deviation. It is the universe's version of rest. To understand why falling forever is stable, remember that a planet in orbit experiences no net force. Yes, gravity pulls inward, but that pull is exactly matched by the sideways motion of the planet's inertia. These two influences cancel each other in a dynamic equilibrium. The result is a constant fall that never completes, an endless loop where motion is effortless and secure. This is why orbits do not require engines. They do not decay under ideal conditions. They do not need correction. Once a world settles into the right speed and distance, it can remain there for billions of years, tracing the same quiet arc again and again. Earth has been doing this for nearly 4.5 billion years. It will continue for billions more. It is easy to imagine orbits as delicate things, vulnerable to disruption. But in truth, orbits are resilient. A small disturbance, a passing comet, a gravitational nudge will not break them. Instead, the orbit naturally reshapes itself, forming a new ellipse that still obeys the same laws, the same balance. Unless a disturbance is enormous, on the scale of entire worlds colliding or stars passing dangerously close, the orbit does not break. It simply redefines itself. This resilience is written into the mathematics of celestial mechanics. Newton's laws show that any stable orbit, circular or elliptical, is a bound state of energy. The planet has just the right combination of kinetic and potential energy to remain tethered indefinitely. Even Einstein's geometry of spacetime confirms this stability. An object in free fall around a massive body follows a geodesic, a natural persistent path that requires no intervention to maintain. Orbit is not a state of conflict. It is the path of least resistance. In the cosmic hierarchy, falling forever is the most peaceful fate available. Consider the alternatives. A planet without enough sideways motion spirals inward, eventually being consumed by the star. A planet with too much speed escapes, drifting into interstellar darkness as a rogue world. These fates are imbalanced, outcomes of excess or deficiency. But an orbit represents the middle path, the perfect balance where energy and motion align with the curvature of spacetime. This balance is not stillness, it is motion refined into stability. The same principle applies throughout the universe. Moons orbit planets, planets orbit stars, stars orbit the centers of galaxies. Galaxies orbit within clusters. Even within atoms, electrons inhabit regions defined not by stillness, but by stable patterns of motion in quantum fields. Everywhere we look, stability emerges not from stopping, but from settling into the right motion. Nature prefers flow over freeze, balance over immobility. This is why galaxies spin like cosmic pinwheels, why stars orbit in spiral arms, why rings form around giant planets. Motion is not a disturbance, it is the architecture of gravity. To fall forever is not to rush downward, it is to move in harmony with the shape of the cosmos. Earth's orbit around the sun is not a circular track, not a closed loop drawn on some imaginary grid. It is a freefall path, maintained by an ancient inheritance of momentum. It requires no effort from Earth, no conscious correction, no external stabilizer. It is simply the geometry dictated by the sun's mass and Earth's motion. Even the variability of the orbit, its slight stretch, its tiny shifts over millennia, does not undermine this stability. These natural variations integrate into the pattern. The orbit breathes, but does not break. The fall adjusts, but does not collapse. The stability is robust, not fragile. You can see the effect of this stability in the everyday world, the consistency of seasons, the predictability of eclipses, the reliability of celestial cycles. Our calendars, our tides, our climate, all arise from Earth's long, steady fall through space. We orient our sense of time around the rhythm of this orbit. We build our years upon it. We measure human history by its repetitions. The constancy you feel, the sense that the world is anchored, is not the absence of motion. It is the presence of reliable motion. In a universe filled with flux, Earth's orbit is a quiet promise of endurance. Even the sun's eventual evolution will not immediately disrupt this balance. In 5 billion years, when the sun swells into a red giant, Earth's orbit may drift outward as the sun loses mass. The falling path may widen. But until that distant transformation, Earth's orbit remains one of the most stable structures in the solar system. The long, gentle fall is not an accident. It is the natural resting state of a world shaped by gravity and motion. When you stand under the sky and watch the stars drift shoreward over the horizon, you are witnessing the effect of this stability. The turning of the Earth, the orbit around the sun, the year's cycle, they are predictable not because the universe forces them to be, but because the orbit is the easiest, simplest path Earth can take. And there is something deeply peaceful in this, that stability is not stillness, that falling is not failing, that motion is not chaos. The universe finds equilibrium not by stopping planets, but by giving them just the right amount of freedom. Earth falls forever because forever falling is the most natural, balanced state gravity can offer. And as this chapter of our journey closes, a final, gentle question rises like the first light of dawn. If falling forever is how worlds find stability, then what does that tell us about our own place in the vast, moving universe? We'll settle into that thought as we drift toward the outro. The Earth is still falling right now, quietly, steadily, endlessly, around a star that carries us through the galaxy, through time, through the deep architecture of space-time itself. And as you breathe here in this small moment, all of those motions continue without effort, without strain, without noise. The universe moves in silence, and you are part of that silence. Everything we explored, the illusion of falling, the balance of gravity and momentum, the ancient spin of the early solar system, the hidden curvature of space-time, the slow pulse of the seasons, flows together into one simple truth. The world beneath you is held by laws older than memory, older than Earth, older than the stars themselves. You are carried by a stability so deep and gentle that you never feel it, yet it shapes every sunrise and every year of your life. There is a certain comfort in knowing that motion does not need to be loud to be powerful, that balance does not need to be still to be calm, that falling, when guided by the quiet hands of gravity and geometry, becomes something safe, predictable, enduring, and beautifully continuous. As you settle into rest, remember that you live on a world perfectly set into its path, a world that has followed this orbit for billions of years and will continue for billions more, a world that drifts through space with a steadiness so complete that your body cannot even sense it. You are held by that steadiness. You are part of that cosmic rhythm. Thank you for sharing this quiet journey through motion and meaning. If these gentle explorations bring you even a moment of peace, I'm deeply grateful you're here. Your soft like, your quiet subscription, your presence, they mean more than you know. Now let your thoughts settle. Let the motion fade into stillness. Let the calm of the cosmos surround you. And as the world continues its endless, peaceful fall through space, may you drift into a deep, restful sleep.